Hi, I'm Mark, the electronic engineer, and welcome to my channel. Hi, I'm Mark, the electronic engineer, and welcome to my channel. Today I want to show you 3 different ways of sampling audio with your microcontroller, your ESP32 in this case, and sometimes even with a standard Arduino. There are several ways. I know 3. And first of all, let me tell you about sampling audio. Basically, what you want to do on your microcontroller, you have an audio input. In my case, it's a line audio directly from a audio system. I'm interested in mono. Stereo, of course, is possible, but it's not as interesting because I mix the channels together in my electronics, and then I apply both to the line input, and I want to see a spectrum analysis on a display. I'm interested in the frequency of audio, say 20 to 20 kilohertz, and my FFT analysis will give out several frequency bins, 8, 16, 32, maybe even more, and each bin will represent the frequency bandwidth. Most important, it has to be fast enough to keep up with the audio signal without a noticeable delay. You don't want to be processing your audio while the display is not updated. You get a display that's slower than the music, because then it's noticeable, and that's of course not what we want. There are several factors you have to consider for spectrum analysis. Sampling, of course, the number of samples and the sampling frequency will affect the time your system will need to do a proper analysis. And another factor that affects your time are the number of frequency bins, the containers, the number of samples, and your general settings for your FFT. For example, do you want to use a DC offset that you have to remove, or do you want some data processing before you give out the output? It will all affect your timing, and the more processing you do, the more time you need, of course. Then the data processing itself, once the FFT analysis has your data, what are you going to do with the data? Is it ready to be sent to your display, or do you need to do some data modifications before you can visualize it? And of course the visualization of the display itself, user interface, web interface, subroutines, all is related, and all will be a factor in your timing. Of course, the ESP32 has dual cores, so you might be able to split up some tasks over different cores. But basically, we can already win a lot of time in the way we analyze our data, or we acquire our samples. And there are several ways. I'm going to describe 3 of them. Several ways to get your samples. First, it's important to know a little bit about sampling. There's a Nyquist Theorem, which basically says that whatever signal you want to sample, make sure that your sampling frequency is at least twice higher than your highest frequency in your signal. So if I want to sample a 10 kilo signal, I should have a sample frequency of at least 20 kilohertz. This is a photo Scott Marley made, and it shows exactly what happens when you sample at the wrong frequencies. Just to give you an idea, if you want to know more about it, please, I suggest you watch his video. The link is below, and he will give you a much more detailed description of what's going on. Briefly, it comes down to this. Imagine those lines here are the moments you're going to sample, so the 10 kilohertz signal, and these are actually the signals I want to sample. Now imagine I have an audio signal of 2 kilohertz, and the red dots where I get my sample represents the signal more or less. So if you connect the dots, you see sort of a sine wave. For the 5 kilohertz, that's similar. It's a sawtooth almost, but it still shows the same frequencies. However, when I sample a 10 kilohertz signal with a 10 kilohertz sampling signal, then this is what happens. The dots always are acquired at the same spot, and then when you connect the dots, all you get is a line and no more frequency is visible. Of course, that's not what we want. Again, if you want to know more about this, take a look at Scott's video. The link is below. The first way of sampling is the easiest way, and it's easiest to try. It's a sequential sampling, and basically what you do is in a loop in your main there's for an X loop in which you take a number of samples, in this case 128. I take 108 to 128 samples, put them in a buffer, and then I process the data from the buffer. However, there's a little catch. I don't want to capture the 128 samples as fast as possible, but I want to sample each interval, I want to acquire each sample at an interval of, in this case, 10 kilohertz. So what I'll do is I look at the timer when I start, I do my analog reading, and then I look at the timer again, and are we already in the next cycle of my 10 kilohertz, or do we need to wait? So basically I'm doing nothing until I'm at the 10 kilohertz and I can take my next sample, and I do that for 128 samples in this case, and then I process. This works. However, this is quite time consuming because I have to wait for 128 samples, or maybe I want to have 1024 samples, and then I have to wait even longer. And during that time there's nothing much I can do, because I still need to process the data and then display it. Although I can do other things, I cannot process my data. There's a certain amount of time it takes, and if I have a large display which also needs time, then what can happen is that your visualization is no longer in line with your audio signal, and there's a visible delay. That's not what we want. So there's a better way. And one way to do it is using interrupt, an interrupt driven readout. Basically what you do is you set a timer at a fixed frequency, your sample frequency, and every time the timer generates an interrupt, you read your analog signal stored in a buffer. Then when the buffer is full, you set a flag, so your main loop or subroutine knows the buffer can be processed. Let me tell you more about it. Now, basically, an interrupt-driven readout is not that hard to understand. What I have is a timer that will generate an interrupt. The timer is set to generate an interrupt at a sample frequency, in this case 10 kilohertz. So every 10 kilohertz the interrupt is called upon, and first I look at a buffer flag which tells me the buffer is not full. So in that case I will get an ADC reading. I store it in my buffer counter. I increase the buffer counter, and in case the buffer counter is full I will set a flag so my main routine knows the buffer is full. And the next interrupt, the same thing repeats. So in the end my buffer will contain, in this case, 128 samples. Now in the main loop I look at that buffer. When the buffer is empty, it just skips this part and goes on to the whatever is next. But if the buffer flag is set, it means the buffer is full and ready to be read out. Then what I do, first I copy the working buffer into the read buffer into a working buffer, and I clear my buffer flag. I reset my buffer counter. Now now we have copied the buffer with the IDC values into a working buffer, and the reason I do that is from now on, whatever I do here, I do to the working buffer and not to my read ADC buffer. In fact, the read ADC buffer can be filled all over again, so whatever time I'm wasting here doing whatever, and during that same time the buffer is already being filled. So as soon as this part is processed, I go on reading the buffer again, which saves a lot of time. Now the third way I know is an I2S driven sampling. The method I showed you before with the interrupts, it's a tremendous improvement from the sequential reading method. However, it's also processor time consuming, especially if you're sampling audio signals of say 18 kilohertz, so you will be sampling at 36 kilohertz. Then it's a lot of interrupts and it will take up a lot of processing power, which might affect the rest of your program. It's quite a load. The ESP32, however, has a I2S driver on board, and it's connected directly to its ADC components. And by using the ITS, we can use multiple buffers. The principle is more or less the same with the interrupt version, only it's all self-regulated. It has multiple buffers, so whatever time I'm losing filling one buffer or doing other things while the buffer is already full, instead of waiting doing nothing till my buffer is empty again, it just takes out the next buffer and starts filling it. You can set 2 or more buffers, which is convenient, and you have 1024 samples per buffer. It's actually designed for audio, so it's good for high-speed sampling, and it's well, basically it's built for audio, so why not use it? And oh, I went a bit too fast, sorry. What we do actually, in your setup, of course, first you have to initialize the I2S driver, which is this part. Okay, so basically what you do is you send a piece of settings to your driver so it knows how to process and how to proceed. It says here use the internal ADC. You could also use an external ADC or a microphone, but we don't need that right now. Sampling frequency, so it knows when to generate interrupts to take samples. A buffer count, you can use 2 or more buffers, 4, 8. The samples per buffer, 512, 1024, 16, 32, you name it. And then I do some initializing of the driver, which it also is tested, and when all is right, then it will give me a feedback in the serial port and output. But when it's all initialized, then basically it says here audio input setup completed, continues, and then we go to our main loop. Now in your loop, which is basically the main, I take my samples here. Basically what I tell them to do is read bytes, samples and sample block, and basically what it does, it doesn't read from the ADC right now, but it reads from the buffer. In the background it's continuously filling out the buffers with ADC samples, and here it's just I take a chunk of buffer and I process it, and that saves a lot of time because it's ready. It's already waiting for me. I just take the data, I continue, and I process it. In this case, I just print it. This program you can actually run, and you can see the result directly to your serial port, which I will include, of course, so you can try it for yourself. Let me see if I had a little output. yeah, here it is. Basically, what the program does, it's initialize. This is my default debugging, and then it says driver initialize, and it starts spitting out the ADC that I read from the buffers. One but, however, you see zeros here. That's not correct. They should have spit out 8 samples per line. This is a bug in the I2S driver, and I already raised the flag at GitHub, and someone will look into that shortly, I hope. Of course, you can do a workaround, but it's not really important for this demo. The schedule I wrote for this example was not completely my doing. It was based on a great tutorial written by Atomic14. Check out his channel below. And also Dave Plummer helped me a lot indirectly, because he uploaded a video on his take on the spectrum analyzer using FFT, and he shared his code, and he explained a bit about it, so thanks for that. And of course there is Scott Marley, who did another great program on FFT on an ESP32. All of them contributed directly or indirectly, maybe without their knowing, to this video, and that's what we do it for, right? To help each other. Thanks again, and I hope to see you soon.